So this displacement triangle, that's what we're going to call this thing right here. And it is a vector diagram, given that we have a vector like this, tail to tip with a vector like that. And as we learned early on in the course, if you put any two vectors tail to tip, the resultant vector is a vector drawn from the tail of the first vector to the tip of the last one. And so we're going to build the range equation as it says up here in the top. And this vector triangle refers to that. Now, the interesting thing about this vector triangle is it doesn't appear in very many textbooks. And when it does, they don't really use it to its full potential like we're going to use it this week in solving some two-dimensional problems. So that's just the basics of what you have here. Now, some other things. V naught t, what kind of quantity do you get when you multiply velocity times time? Displacement, or a distance, if you will, and this one would be a straight line distance, obviously. Look over here. Little g, which we've found experimentally and read that it is equal to a constant value, is an acceleration. Acceleration has units of meters per second squared. Time squared is second squared. So what would the units be of 1/2 gt squared? You have meters per second squared times second squared. Table 2, somebody save me. Meters per second squared times second squared will give you meters, which is distance. So this is great. It's really important that when you add vectors, they be the same kind of quantity. Otherwise, they don't add. Sort of like numbers don't add unless they're referring to the same whole, part-whole relationship. All right. So we have a distance plus a distance, which means this last thing should be a distance, which is why I use the letter D. And then there is this angle theta that separates this initial vector that it goes. Now, if it's a projectile, we're probably talking about something like kicking a football off the ground, or just like we just saw in the PhET simulation, a cannon shooting something. Those are typical kinds of problems that we'll solve. And so there's an initial speed that ball has. Now, what happens to something as soon as it leaves the event that caused its motion? So if I kick it, the ball, or I blast the cannon, there was a force that produced that motion, correct? So as soon as that force is no longer in contact with the object, and it's the cause of this motion, what immediately happens for an object in free fall? What immediately happens to its speed? Table 1, somebody save me. Gets pulled down or starts slowing down, just like that one problem where we threw a ball straight up. As soon as it leaves the hand, it's slowing down. Comes to a stop, and then gravity gives it all that speed back. But the whole time, gravity was accelerating it, and in one direction, it was accelerating it down, and in the other direction, it's still accelerating it down. Just it had to gobble up some of that speed. So when this object gets moving, what happens is this part of the puzzle is doing this work, quite literally. In fact, soon we'll be calling work done by gravity. It's a force that causes a displacement, energy, if you will. All right, so it's coming soon to a theater near you. All right, but for now, we're just going to try to work this out mathematically. So this triangle represents physical reality in terms of distances uh, that are caused or at least linked to speed and acceleration stuff, the stuff kinematic stuff that we've been studying so far in the course. So that's your overview of what this triangle represents and how it's put together. So what I want to do now is let's do some math, everybody's favorite thing. That's why I took an algebra course and trig, pre-calc, whatever it was. So now what I'd like you to do is write the sine, cosine, and tangent ratios for this displacement triangle, just as they are symbolically. You can do some simplifications if you want, but don't plug any new numbers in. All right, so let's pause for a minute and see if you can pull that off. So if we were to say do the sine of theta, that would be opposite over hypotenuse, and the opposite is 1/2 gt squared. The hypotenuse is v naught t, and that should simplify down to, since these one of those t's will kill that t, I could write this as gt over 2 v naught if I wanted to. That would be about as simple as I can make the sine. The cosine of theta would be adjacent over hypotenuse, d over v naught t. And the tangent of theta would be the opposite over the adjacent. And really that would just get no simpler than that if we were to go at it. Right? So then this next problem wants us to solve the cosine ratio for time and substitute it into the other two ratios. So if I just swap the t and the cosine theta, which is the thing to do there, that's what we get. So if I substitute that into the other two ratios, so sine of theta would be g times, put d over v naught cosine theta in there. Actually, I'm going to redo that in color just to keep the theme going here. So d over v naught cosine theta, and that would be over 2v naught. And if you simplify all of this, you'll get gd over 2 v naught squared cosine theta. And the tangent theta would be g over 2d, and then we would be squaring this time, so I'd have a d squared over a v naught squared cosine squared theta. Just going to kind of square it in place there. And then that would, one of those is going to kill one of those. And you would have GD over 2 tangent theta cosine squared theta. And tangent is sine over cosine. So that means you could simplify this one step further. 2 sine theta cosine theta. Oh, I left the v naught squared out of there. Let me, like something's missing here. So those are just going to go back. You can squeeze that in at the end or something if you want. V naught squared. Oh, I really need to watch my work here. I apologize if you're taking notes in pen, but we need to only go that far with it for the moment. I'm getting ahead of myself in there. So we get rid of time in the other two by substituting it out in those. And then we are going to solve both of these for d. So let's take this first one for sine. D would be, so if I take all that stuff that's on the denominator and multiply it through on the other side, I'll get 2 v naught squared cosine theta sine theta, and all of that's going to be over g. So in one sense, we could sort of group things a little bit differently according to, in fact, what I'm going to do here, I'm going to group things according to, I'm going to separate numbers from quantity. All right. So now all the quantities are grouped together in that first factor, and then all those number stuff, because 2, sine, cosine, those are just numbers. They're not anything else. Then the pull the d out from the tangent, and I'll get similar sort of thing. So I'll get v squared over g, and that 2 will pop up there, tangent theta cosine squared theta. And again, because tangent is sine over cosine, this cosine will kill one of those, and you get the same thing. So interesting. Plugging time into the other two equations generates an equation for distance that's identical. This first page, and you look at this diagram, you would want to, how would I redraw this so that it lands above ground? So I want you to take a swing at that. Think about this first. So first thing I want to do is just, in a normal situation, the path of a projectile is going to do something like this. It'll start off here, but as soon as it starts falling, and it does that. Okay? So if we were talking about a projectile that was, say, going to land above ground, so let's say, it was above ground, some height h. Well, if this thing had a little bit more speed, then it could collide here with something, a wall, a hoop, anything, because if it wasn't for something at that height, it would keep on going like that. But there could be anything here. There could be a building here. There could be a hill. There's all sorts of things that could be in the way and would prevent it from going its full range. Because obviously, if it wasn't for something being in the way on that green path, wouldn't it go farther? And that triangle would be something more like this. Okay? And your range would be a little bit longer. So we can so little math, whoops, went to the distance or range over V naught cosine theta. We have a little bit of work to do here, but I want to walk through it with you. So up here, just say, you know, this displacement triangle models two-dimensional projectile motion of an object that returns to the same level that it started. All right. So the standard classical range equation refers to that and that alone. And if you wanted to have a range equation that referred to any other path besides returning to the same elevation that it started at, you would have to modify the range equation. You won't find that in any textbook that I know of, but the way that we're going to use this displacement triangle, we can get around that problem. And we'll show the easy way, which is using this tool, and then we'll show a more complicated solution to a problem where you don't get to use that and you have to equation hunt. All right. So let's try to get at this here. And so what I want to try to do is get you to do this right here. So you're going to redraw the triangle with its vector labels such that it models some height h where the projectile lands above ground. So if you go back to, we'll get back to this in a minute. Add me a page in here. So if we go back to this, zoom that out a little bit. Then we can come on to this next spot here. So write a tangent ratio for the triangle in step 4. So that would have been what we just did, because the numbering got goofed up here now that I realize that. And then change D to R for horizontal range. So we have some things to do. Write a tangent ratio. So let's, then our next fish to fry, change D for displacement to R for horizontal range. Then clear fractions, wrong direction. And then isolate the term representing the gravitational interaction portion of the vertical leg of the triangle. So it's a lot of words. Isolate the term. In algebra, if it's a term, it's separated by a plus or minus or equal sign. The term that has gravity in it is the gt squared. G is a factor. T squared is a factor. Gt squared is the term involving that horizontal leg. And then you can consider yourself checked with me, all right? Since we're walking through this together. Now, solve the original cosine ratio from step 1 for time. We already did that and substituted into the equation from this step here. So this is supposed to be 5. All right, more on that later. So let's substitute time. If you remember, time was equal to this comes from the cosine relationship. So we can have a displacement triangle and we could think of it that way. And what this is doing, whether you realize it or not, is I'm basically putting something with length in the way of what gravity would do. Okay? Because it's still going to have a horizontal range, correct? So what you wouldn't want to do is do that, because that's not horizontal range. That's a not horizontal range. That's some other distance. Okay? It would be a legitimate distance between the starting point and where it landed, but it wouldn't be the range, because the range is by definition the horizontal displacement. It's the x part of the object's actual displacement. So that blue thing would be the actual displacement from where it started to where it ended, but range isn't the total displacement of the object unless it's all at ground level. So that little distinction there in what we do. So what we have now is a new vector triangle like this. Here's the nice thing about this version. If h is 0, you have the range equation. But if h is not 0, if it's a plus or a minus value, then your trigonometry gets a little more complicated. All right? Get at it here. So here's theta. So the tangent of theta would be 1/2 gt squared plus h over d. So it's a simple enough tangent ratio given what we have. Okay, so I'll change these to r. That's simple enough. It's getting us closer to the classical. So clearing fractions, before I can clear fractions in the numerator, I got to clear out that denominator. So get a pin back here. So r tangent theta equals 1/2 gt squared plus h. Then if I wanted to, I could multiply everything through by 2. And that would clear one fraction. So 2r tangent theta equals gt squared plus 2h. The lingo there, and we want to isolate that. So now I'm going to have gt squared will equal 2r tan theta minus 2h. So time squared, so that would be r squared over v naught squared cosine squared theta. So you get when you square r over v naught cosine theta. And this side remains the same. And if you're, and then it says simplify that so there are no fractions. All right, so everything's got to get multiplied through by a v naught cosine squared theta. That's the drill. So that's easy on the left-hand side. And so 2 v naught squared cosine squared theta tan theta r minus 2 v naught squared h cosine squared theta. I know this is exciting stuff. You guys are, please hold your applause if I have to call campus police to contain this riot. So, yay, we have this monstrosity. What I hope you recognize is that basically, because I have an r squared and an r, this is a quadratic equation. Reason why is that's a constant, that's a constant, the initial speed is constant, the angle is constant, the height above ground is constant. Basically, you have a bunch of constants times something that can change based on some constant initial speed that you give. So this is a quadratic equation. And so in step 4, it tells you to distribute this so you have it in that form so that's equal to 0, because if you, I'm going to go ahead and change this to sine theta cosine theta because that tangent and the cosine work down to that. We already did that on a different part here. Take that back. This needs to be plus. There we go. Now I have a quadratic function. And these things I'm highlighting will be the A, B, C in the quadratic function. And then in step number 5, I tell you to use the quadratic formula to obtain a function for horizontal range. And I give you the note that this could take a while and could be some of the most fun you've ever had this century. However, because I am a nice guy and it's Monday, I am not going to force you to work that out on screen. Main reason for that, this ain't a math course. This is a physics course. So at this point, the physics is done. So to use our physics is done at this point. And now it's a math problem.